we will discuss an aspect of diffusion that we have not discussed so far, and that is an average velocity that is generated by the flow, relative flow of species. Okay. You recall when we initially did our discussion, I said that if you have a fluid in which there is two different types of molecules, okay, and there is a gradient in the concentration of these molecules, okay, and each of these molecules is having some fluctuating velocity. There will be a net motion of molecules from one side to the other of one species and motion in the opposite direction of the other species. Okay. And there will be net zero mass transfer provided the masses of the two molecules are the same. This would also be true if one of the molecules, the concentration or the number of molecules or the concentration of one of the species is much smaller than that of the other species, what we call a tracer diffusion, that is diffusion of one species which is present in very small amount relative to the other species, so that the motion of that one species does not cause a motion of the entire mass as a whole. Okay. If the molecules had different molecular masses, then even if equal numbers of molecules travel from below to above and from above to below, the fact that the molecular masses are different can generate a net fluid flow. Okay. And that has to be taken into account when we define the diffusion fluxes. Okay. And that is what is called that is the issue in multi-component diffusion, that when you when species move relative to each other, even though the number of molecules of each species moving up and down may the number density may not be different, there could be a net motion of mass because the mass is different. Okay. And in that case, in the case of multi-component diffusion, we have to incorporate the total flux and the fluxes of the individual molecules relative to the velocity of the average mass velocity or the average molar velocity. Okay. So, I will discuss this only for binary diffusion. I will not go into the details of multi-component diffusion. That is a more complicated subject, and it is necessary to discuss some equilibrium thermodynamics before we can discuss the subject of multi-component diffusion. Okay. So, I will just talk about mass diffusion. The densities in mass diffusion can be expressed in one of two ways. One is the mass density and the other is the molar density. The flow velocity is defined based upon the mass density, okay, because it is the flow velocity is the velocity of the center of mass. Okay. So, for momentum transfer, it is necessary to use the mass averaged velocity for defining the velocity field. However, there are situations where the mole average velocity is preferable, especially in situations like, for example, in a gas. In a gas at constant pressure, the number density of molecules is a constant. Okay. If you have multiple species, the number density, the total number density of all the species put together is a constant. Okay. Or in other words, the total molar density is a constant, because that is what is related to the ratio of pressure and temperature, okay, in ideal gas law. And therefore, in those situations it is better to talk about a molar density. However, when you define velocity fields, it is always defined in terms of the mass density. Okay. So, let me first start by defining quantities based upon the mass density. Okay. The total mass density is equal to the mass densities of the two species for a binary mixture. Okay. The total mass density, mass per unit volume, is the mass density of the sum of the mass densities of the two species. Okay. So, rho is equal to Ca plus Cb. The mass fractions are defined as Ca by rho and Wb is equal to Cb by rho. Okay. These are the definitions of the mass fractions of the two species. Okay. The total momentum, okay, rho times Vz, okay, where Vz is the mass average velocity, is equal to the concentration of A times the species average velocity of A plus the concentration of B times the species average velocity of B. Okay. Okay, the total momentum. Okay. This can also be written as the sum of the fluxes, because the convective flux is equal to the concentration times the velocity perpendicular to the surface. In this case, I am taking z as the direction perpendicular to the surface. So, this can also be written as the sum of fluxes Jaz plus Jbz. Okay, this can also be written as the sum of the fluxes. Okay. Now, the constitutive relation for the mass flux, okay, the constitutive relation for the mass flux in binary diffusion. Okay, so, if you recall, we had written the mass flux as minus d dc by dz. Okay, we had written the mass flux as minus d times dc by dz. Okay. In binary diffusion, this flux is written slightly differently. Okay. It is written as minus dAb times rho times dWA by dz. Okay. That is the diffusive part. Okay. That is the diffusive part of the mass flux. Okay. And then there is a convective part, that is the convective part is due to this center of mass velocity. Okay. Okay, the convective part is due to this center of mass velocity plus Wa into rho into Vz. Okay, this is the total flux that includes the convective part and the diffusive part. Okay. Okay. So, this convective part is just the concentration of A into Vz, that is the Vz is the center of mass velocity. Okay. So, concentration of A into the center of mass velocity is gives you the convective flux. Okay. Okay. And now this rho Vz, I can write it in terms of the fluxes using this relation. Okay. I can use this relation to write it in terms of the fluxes. Okay. So, is equal to minus dAb rho dWA by dz plus WA into JAZ plus JBZ. Okay. You can see that since the center of mass velocity depends upon the fluxes of the two species, this becomes an implicit equation for the fluxes. Okay. So, the flux of A depends upon the flux of B and vice versa. Okay. Here dAb is the diffusion coefficient, the diffusion of the species A in a mixture containing A and B. Okay. The diffusion coefficient is the diffusion of species A in a mixture containing the species A and B. Okay. Similarly, I can write for the species B minus dBA rho dWB by dz plus WB into JAZ plus JBZ. Okay. And obviously, since A and B are mass fractions, it follows that WA plus WB is equal to 1. Okay. The fraction of A molecules plus the fraction of B molecules has to add to 1 in a binary mixture. Okay. So, these are the relations for the fluxes. Okay. And it has some implications for the way in which for the diffusion coefficients. Okay. Note that since dWA plus WB equal to 1, this implies that dWA by dz plus dWB by dz is equal to 0. Okay. Okay. If you take the derivatives of the left and the right sides with respect to z, the sum of the derivatives has to be equal to 0. Okay. So, if I add up these two species, okay, if I add up these two equations, I will get on the left side is equal to minus rho into dAB dWA by dZ plus d plus WA plus WB into JAZ plus JBZ. Okay, just adding up those two expressions. This is equal to 1, okay, this is equal to 1, okay, and therefore, these two terms will cancel out on the left and the right sides. Okay. And from this relationship, we know that dWA by dZ minus dW by is equal plus dWB by dZ is equal to 1. So, I can write this as 0 is equal to minus rho dWA by dZ into dAB plus dBA. I am sorry, there is a negative sign here. Okay. And you can see just from this, the diffusion coefficients dAB and dBA have to both be equal. Okay. Okay, just from this consistency condition for the fluxes. Okay. And that follows because we have written the flux in this form in terms of the mass fractions rather than the concentration, okay, in terms of gradients of the mass fraction rather than in terms of the gradients of the concentration. Okay. Now, to proceed further, okay, if we want to further go and solve this equation, these equations, we need to know something about how the sum of these two fluxes, okay, we need to have some further information about the sum of these two fluxes. Okay. And that of course depends upon the problem at hand, okay, and I will illustrate that with an example shortly. But let me just go on to defining the mole average velocities. Okay. Okay. This is now in terms of moles or number of molecules rather than in terms of mass. Okay. Okay. The molar concentration, total molar concentration I will use the notation C, okay, for the total molar concentration, and I will use the mole fraction capital WA and capital WB. Okay. Capital WA and capital WB, okay, and the molar fluxes okay. This is moles per area per time. I will write it as JAZ capital and JBZ. Okay. Then the total molar averaged velocity. Okay. Note that this velocity that we have here, okay, this Vz that we have here is the mass averaged velocity. Okay, it is based upon the mass densities of the two species. This is a molar average velocity, okay, and it is defined by the relation C times capital V of Z, okay, is equal to the molar concentration of A times VAZ plus molar concentration of B times VBZ. Okay. and if I divide throughout by the total concentration, I will find that V z is equal to W A V A z plus W B V B z, okay, exactly analogous to the mass averaged quantities. Okay. And of course, since these are fractions, you have W A plus W B is equal to 1. Okay. The constitutive relation for the molar flux, okay, the constitutive relation for the molar flux is written as J A z is equal to, in a similar manner, minus d A B times C times d W A by d z, okay, plus W A into C times V z, okay, that is due to the motion of the center of mass, okay, the concentration of A times the center of mass velocity, okay. And this C times V z can be written in terms of the species averaged again, okay. Note that this is also equal to J A z plus J B z. These are the molar fluxes, okay. These are the molar fluxes J A z and J B z, okay. Okay, therefore, this can be written as minus d A B C d W A by d z plus W A into J A z plus J B z. Okay. Similarly, for species B, this would be written as J B is equal to minus D A B C And since we have the relation W A plus W B equals 1 and d W A by d z plus d W B by d z is equal to 0, okay, we have these two relations. Therefore, we can add up these two equations again, and what you will find is that d A B is equal to d B A in a manner very similar to what we had done for the mass average velocity. Okay. So, these are the constitutive relations, okay, for the mole averaged flux, okay, and for the mass averaged flux. Okay, the mass averaged flux, we have exactly the same form. The diffusion coefficients have the same dimension, except that in one case you are taking it with respect to the mass density, in the other case you are taking it with respect to the molar density. Okay. As I said, the mass density is of course what is used for defining the flow velocity or the center of mass velocity. Okay. However, the mole average description is often very useful in situations where these two are simply related. Okay. So, for example, if you had a situation where one species velocity was equal to 0, okay, if the velocity of one species was equal to 0, then you could just solve this explicitly for the other species. You could also have situations where reactions take place, okay, so that the fluxes of these two species have to be simply related to each other. Okay. In that case also the mole average description is the more appropriate one. Okay. So, that is the reason why binary diffusion is often problems in binary diffusion are often solved using the molar averaging procedure. Okay. So, especially in gases, okay, where you have in gases where the sum of the moles of all of the species has to be a constant. The sum of the masses does not have to be a constant. Okay. In the ideal gas limit, where the pressure and temperature, the ratio of pressure and temperature, absolute temperature is related to the total number of moles. Okay. So, in gases or in cases where there is reaction taking place, so that the different species have to, the ratios of the moles of different species are simply related, it is more appropriate to work in terms of mole averaged quantities. Okay. And I will demonstrate that with a couple of examples. Okay. The first is the evaporation of water from a thin tube. Okay. Water in a thin tube is evaporating because there is dry air that is blowing across. Okay. And this total distance is, let us say, 15 centimeters. Okay. And we want to know what is the evaporation rate of water, that is how much does the water height decrease with time due to this evaporation. Okay. At temperature is equal to 25 degrees centigrade, where the vapor pressure of waters is equal to 3.15 kPa. Okay. Kilopascals is the vapor pressure of water. Okay. And the diffusion coefficient of water in air is 2.2 into 10 power minus 5 meter square per second. As I told you earlier, the diffusion coefficient of most common species are of the order of 10 power minus 5 meter square per second. Okay. So, here the saturation concentration of water at the surface is Cs, okay, and in dry air the concentration is equal to 0. Okay, the concentration of water is equal to 0, or the mole fraction of water is equal to 0. Okay, so, we are going to solve this using the molar averaging procedure. Okay. Now, the density of water is about 1000 kilograms per meter cubed. Okay. So, as the water evaporates, right, the volume of water that is coming out, okay, the density of water vapor is about 800 times less than the density of liquid water. Okay. So, there is an expansion by a factor of approximately 1000 when water evaporates. Okay. So, the volume of water coming out, okay, the volume of water vapor that comes out is going to be 800 to 1000 times the volume of liquid water that has evaporated. Okay. As the evaporation takes place, the level of the water decreases because water has evaporated, and as the level of water decreases, there has to be some flow of air into the tube in order to occupy the space that has been evacuated by the water liquid evaporation. However, the volume of the liquid that is evaporating is 1000 times less than the volume of the vapor that is coming out. Therefore, there is a flux of water vapor out which is 1000 times higher than the flux of air that has to come in order to compensate for the liquid level decrease. And therefore, we can neglect the flux of air inwards in comparison to the flux of water that is going out. Okay. So, that is the first one. Okay. So, therefore, if I write the diffusion equation, okay, for the flux J W in the z direction is equal to minus C d, okay, the diffusion coefficient of water in air, d W water by dz, okay, that is the flux, plus W of water into the flux of water plus the flux of air. Okay. If you recall, that is the equation that we had for the flux, okay, for the two species. Okay. So, this is the equation for the flux, and we know that the flux of air is much smaller than the flux of water by a factor of 1000 or so. Therefore, the equation that I get for the flux is just that J W z is equal to minus C d W a d W by d z plus W into, okay, I should put the subscript z, okay, because I have neglected the flux of air. Okay. Take it to the other side and I get J W z into 1 minus W. Okay. And I divide throughout by 1 minus W and C d W, okay, and I will get J W z is equal to minus C dWA by integrate this once with respect to W. Okay. So, this can be written as JW dz is equal to minus C dWA into dW water by 1 minus the weight the mole fraction of water, okay, 1 minus the mole fraction of water. Okay. Integrate this once and you will get JWZ is equal to JWZ into Z by C dWA is equal to log of 1 minus WW plus some constant of integration, okay, plus some constant of integration. Okay. That constant of integration is determined from the condition that at the surface, okay, if I take this as Z is equal to 0 and this as Z is equal to H, at the surface Z is equal to 0, the weight fraction of water is equal to the saturation concentration. Okay. The saturation concentration is the ratio of the P vapor pressure divided by P atmospheric. Okay. The concentration of water at the surface, okay, the concentration of water at the surface is equal to the total concentration times the mole fraction of water at the surface. The mole fraction of water at the surface is the ratio of the pressure and the atmospheric pressure, okay, which is 3.15 into 10 power 3 pascals divided by 1.013 into 10 power 5 pascals is equal to 3.1 into 10 power minus 2. Okay. That is the mole fraction of water at the surface, okay, at Z is equal to 0. Okay. So, using that you can find out what is the constant in this. At Z is equal to 0, 0 is equal to log of 1 minus WW, okay, plus I 1 minus the saturation concentration. Okay. So, I is equal to minus the log of 1 minus Ws, and my final equation for the flux becomes JWZ Z by C dWA is equal to log of 1 minus the water mole fraction by 1 minus the saturation mole fraction. Okay. And the saturation mole fraction is this one based upon the vapor pressure. Okay. So, this is the final solution. Okay. How do we find the flux? Okay. We know at this height Z is equal to H. At the height Z is equal to H, the concentration, the mole fraction of water is equal to 0. Okay. WW is equal to 0. Okay. Okay. So, the mole fraction of water is equal to Ws at Z is equal to 0 at the surface. It is the saturation mole fraction, and WW is equal to 0 at Z is equal to H. Okay. Therefore, you get JWZ H by C dWA is equal to log of 1 by 1 minus the saturation concentration. Okay. And from this I can get what is the water flux, which is C dWA by H log of 1 by 1 minus Ws. Okay. So, that is the flux, okay, of water. Okay. We will continue this in the next lecture. All we need to do now is to substitute the values of the molar concentration, the diffusion coefficient, the saturation concentration of water, and the total height, and find out the flux. Okay. Once we know what is the flux, then we can calculate what is the rate at which the water is evaporating, okay, what is the rate at which the height is decreasing of the surface. Okay. So, I had defined for you what are mass averaged quantities, molar averaged quantities, and the modification for the constitutive relations for the mass flux and the molar flux. Okay. In binary diffusion, where you have a contribution to the center of mass velocity due to the fluxes of the two species, which in general may have different molecular masses. Okay. The diffusion coefficients are equal, dBA is equal to dAB in both cases, and I had shown you what is the modification to the constitutive relations. And I had started off a problem of the evaporation from a surface. I will continue this in the next lecture and then complete another problem which is related to reactions. I will continue this in the next lecture. I will see you then.